Okay, now we're going to talk about parallel circuits. Just a little safety tip. Don't let your lab assistant turn on the power to the power supply before you're ready. I never did know I could jump that high. All right, thanks a lot, Leslie. Okay, so here we have parallel circuits. Now here we have two 47 ohm parallel circuits. We've got the voltage coming in here and going out there, the plus and minus, right? Ready? So it comes in here, and then I just go straight over to here, and then I split it into the two resistors. This is the splitter right here, this cable right here. And it comes back over here, also splits here, if you will. It comes back together and goes back over there that way. Now, on this case, we're going to turn the power on. And let's set it up to measure voltage again. We'll start with voltage. So we move that guy over there, move this guy all the way over to 20, and now we measure the voltage. Again, it's going to be 10 here because Leslie didn't blow up the power supply, she just blew up my fingers. All right? All right, so there we go, 10. So what is the voltage going to be across the resistors? Well, if we go from here to here, what do you think it's going to be, Stephen?
No, there's going to be the full 10, right?
It's going to be 10, you're right. And it is, it comes out to 10. If we go across the other resistor, it's going to be 10. See, when they're in parallel, all the resistors see the same voltage drop. They have to because right here, this is a wire that goes straight between them. So they're connected together, and right here they're connected together. So they have to see the same. But unlike series, in series, all the resistors saw the same current, but saw different voltage. In parallel, it's the reverse. They see the same voltage, but different currents, or potentially different currents, depending on the resistors. So how do we measure the currents? Well, I got it set up here. Let's move back over to current. Let's put it over to here, onto here, like that. And we flip this over to 200 milliamp. Okay, we'll go to 200 milliamp max. Now, if we want to measure the current, what you do here, we'll measure the total current, and then we just take out this guy right here. Ah, looks like it got welded on. Okay, there it goes. And we want to measure the total current through both resistors. It came out to be too high. What the hell happened? 2 divided by 50. Well, we got 10 volts. Oh yeah, that's. Yeah. Let's put it over here on the. I hope I didn't blow it up. Let's put it on this one here and see if I. Okay. Oh, it was just a small number. Okay. It's saying I've got 4 milliamps. Not sure if I believe that because I got 10 volts. This would be roughly 25. So 10 divided by 25 would be 400 milliamps. Or 40. Something might be off with the scale. Anyway, that's how I would measure the current through the total current. If I want to measure the current through one resistor, let's pick a resistor. Which resistor do you want to pick, Leslie?
The bottom one.
See, I told you I could get her to talk. All right, so we put.
I'm not real, I'm invisible.
All right.
I'm Matt's imaginary friend.
I used to have an imaginary friend when I was a kid, but
I have one.
he beat me up.
Yes, I did.
Okay, so now if we want to measure the current through this resistor right here, I don't know which one Leslie asked for, I didn't care. Okay, what I did is I just broke the circuit over here, I just disconnected that, all right? And what we're going to do is we'll turn the power back on. And now we're going to measure the current from here to here. Now the only way the current has got to go, looks like I got them reversed, it's only going to go through this resistor. It can't go through both resistors anymore based on what I've just completed. I just replaced the wire that went from the node to here. All right? Now does that make sense to you? So this is a critical point. This is different than taking the current measurement. Taking the current measurement here is different than taking the current measurement across these two.
So where are you taking the measurement?
I'm taking the measurement from the node where everything comes in to where it splits off. Right now, the electricity that's going through this resistor is only let's see. it's going through my current meter and then going through this resistor. It's not going through the other resistor at all,
So which resistor are you measuring?
just the bottom one.
Okay.
Because look, I got right here, it's going to the bottom. It's going from this one right here. This is this is where the node, where everything, all the current comes in. And I'm just splitting it off to the part where it only goes to this resistor.
Okay. Can you measure the top one now?
Yeah, I can. Now, the easiest way to do that is to just grab the, well, first we should turn the power off. Grab this guy here and move him here. And now I'm just measuring the current that goes through that resistor. Okay? Now, if you notice, I don't know if you noticed it before, but it's 2.1 for the other one also. It's 2.1 for both of them. 2.1 plus 2 plus 1. 2.1 is, well, 2 plus 2 is 4, right? I know, you didn't think that would come in handy in this class, but it does. 2 plus 2 is 4. Stephen is amazed. Okay? Leslie is like, I think I heard that somewhere before. All right. So we just measured that. Now, so we can measure, if you measure from, if we can turn this thing off, let's put it back all the way it was. If you want to measure the total current, you just measure it from here to here. If you want to measure the current through this resistor, you just measure it from the node, which is right here, to here. If you want to measure the current through this resistor, well, then you have to just switch things around a little bit. But you have to make sure that you're measuring it just through the path that goes through that one resistor. If it's going through both, if it's going to go to both resistors, then you're not measuring the current through one resistor, you're measuring the current through both. Now this gets a little bit more interesting. If let's take this guy out and let's put another resistor in here. This is a 470 ohm one. Okay? So now the currents aren't going to be the same because the resistors aren't the same. Okay? Now the total current is still going to be the voltage divided by the resistance. And you remember how to figure out the resistance for parallel resistors, right? If you don't, look it up. In this case, it turned out to be 2.3 or so. Okay? So now that means that the current going through this resistor plus the current going through this resistor have to be equal to 2.3. Does that make sense to you guys? Okay. Because it's two different paths. We're splitting up the current into two different paths. So now let's take a look at the current through the big resistor, the 470 ohm one. We'll take that off just like we did last time. And we put this on here like that and that. And we get that it's 0.2. I got these things reversed. It should be like this. Should be positive, generally. 0.2. So what was the total current? No, it wasn't 4. It was 2. 2 point something. 2.3. So we'd expect the current, so if hardly any current is going through the big resistor, that means most of the current has to be going through the small resistor. Does that make sense? Okay, so let's find out. We'll turn this off. We move this guy over here. And then we put it in like that, I think. So hardly any current was going through the big resistor. And now look at that, 2.1. So 2.1 plus 0.2 is 2.3. So the whole, hey, come on in. Okay. Come on in. So the whole thing is, the whole current, 2.3, is split up. Some of it goes, the small amount goes to the big resistor, the large amount goes to the small resistor. If you think about that, that makes sense. If you think about it in water, water is going to follow the path of least
Resistance.
Say it louder, Steve.
Resistance.
All right. Does that make sense? All right. I hope you enjoyed this little review for your physics test. It'll be important. Bye.